Good afternoon, students. I'll start the class at 1. So you tell your friends to join by then I'll lock the meeting. After that, I won't be allowing entries. So, good afternoon, students. We'll continue with our previous lecture, which was human error. So, the human error that takes place during a bridge design we'll discuss today, citing it as an example of bridge design. So, the first example that I've cited is human error in bridge design. So, a classical example of human errors, you have to consider the Jorn Bridge, which is at Sweden. So Jorn Bridge is shown in figure 1.9. This is the Jorn Bridge, which is located at Göteborg, Sweden. So the bridge was intended for ship traffic to pass under the bridge midstream as indicated with buoys positioned with the river. So why was this bridge constructed? It was constructed for ship traffic in order so that under the bridge the traffic can pass easily as a midstream and in between the buoys. These are the buoys in between without any ship traffic congestion. So this picture is of John Bridge is just after erection, like after construction, after erection at Göteborg, Sweden. So the fact that the river is equally deep close to the banks of the river and that the captains normally sailing on the river were accustomed to sailing close to the banks rather than midstream in order not to worry about the ship traffic coming in the opposite direction was either not known to the designers of the bridge or not realized as a potential hazard. So what happened with the bridge is that since the river is, as you can see, it is nearly or deeply close to the banks, it is close to the banks, right? So, and that the captains, those who sail the ship, normally they sail on the river and they were accustomed to sailing where close to the banks, like they sail from the sides and not in the midstream. So why they did that? In order to not worry about the ship traffic, so that the ship traffic is not more. So that's the reason they go for the sides and not in the midstream. So, and this was not known to the designers of the bridge and not realized as a potential. So the designers of the bridge did not realize that ship traffic coming from opposite side or going from this side or from coming from both the sides may be a potential hazard. So the result was that what happened was that the bridge, after only a few months in operation, was rammed by a passing ship and collapsed completely into the river as seen in figure 2. So as a result of this, after a few months, the ship, one of the ship which passed by, they rammed, like they hit the bridge, I think in the sides, and the bridge completely collapsed as seen in figure 2 means this one. So this is the John Bridge after collision with the ship in January 1980. The bridge, this one, it completely broke off, as you can see. So subsequently, a new bridge was built on the same location. A new bridge was built on the exact same location, but this time the designers had learned their lesson. But obviously, this time from their previous experience, the designers or the engineers have learned their lesson. And so they decided on a suspension bridge allowing free passage under the bridge over the full width of the river. So that's why they decided for a suspension bridge which allowed free passage under the bridge. So the risk of ship collision was thus treated by a mitigation measure. So the risks that may take place by ship collision, it was treated immediately as a mitigation measure by erecting a suspension bridge. Next, a review of the reported failures. The experiences from failure of technical installations and activities in general provide a valuable knowledge base. First of all, this information gives an overview of the safety and reliability of such installations and activities as performed in accordance with the present or past engineering practice and therefore also gives indications as to where this might be improved. So, on our review of reported failures that has been reported, so experiences from failures mainly occurs due to technical installations, wrong installation process and activities, and this provides the failure of technical installations and activities in general provides a rather after valuable knowledge. Like after the incident took place, you get the knowledge of the same how this failure of technical installation or activities took place. So this information it gives an overview of the safety and reliability of how such installations should be done or performed in accordance with the present engineering and past engineering practice. And therefore, it also gives an indication as to where this might be improved. So, furthermore, if studied carefully, the information may provide an understanding of the important hazard scenarios for different types of installations and possible hazards. So, this information that we obtain from the failure of installations and activities, it gives us an important understanding about the different hazard scenarios for different types of installations and the possible hazard that may take place. Thus, a basis is provided for studying the associated risks in more detail and not least understanding how risk treatment may be efficiently implemented. Therefore, in the following, an overview of given mainly based on the research of Matosek and Skinder 1976 and Stewart and Melchers 1997 concerning the dominating sources of risk for the following: building and bridge structures, dams, offshore structures, pipelines, nuclear power plants, and chemical facilities. So failures of building and bridge structures. So based on a total of 800 reported failures and errors leading to accidents, damages from the area of structural engineering, Matosek and Skinder in 1976 have reported a detailed review of the causes of how the failures and errors might have been counteracted by adequate means of risk treatment measures. So Matosek and Skinder in 1976 reported or reviewed different types of structural failures that took place and also provided risk treatment measures for the same. So in figure 2.1, it is illustrated when in the course of the projects, the failures and errors were discovered for different types of structures. So these are the different types of structure, there is types of construction and the failures that took place, execution, the plain part is the execution, usage is this part and the highlighted part is retrofit, that is disposal. For high-rising buildings, industrial buildings, traffic structures, dams, rest, and all cases. So this illustration of when in the course of the project the failures and errors were discovered were again reviewed by Matosek and Skinder in 1976. So from figure 2.1, it is seen that on average the failures and errors were discovered more or less equally during execution and usage of the structure. So some differences in the distribution between the different types of structures are evident. One explanation to these differences may be attributed or contributed to the human-structure interaction during the period of operation. So clearly, industrial structures suffer mostly from failures and errors during the operation, whereas dam structures with very little interaction with humans during the operation and experience the largest part of failures and errors during the period of execution. In figure 2.2, the relative distribution of causes of the failures and errors is illustrated. So it is seen that the major contributions have origin in structural failures and failures of interim structures used during the execution phases of the projects. So these are also the cause of the majority and incidents leading to loss of lives and injuries and completely dominate the damage costs. So this is figure 2.2, which is the illustration of the relative distribution of the different causes of different accidents or incidents that took place as reviewed by Matosek and Skinder. So structure, fitting, site and installation, technical, interim structure and the rest. That is the remaining part. So structural damage, cause of damages and damage of persons. So in figure 2.3 similarly, the primary causes of structural failures again cited by Stewart and Melchers in 1997 are illustrated. So the primary causes listed here are complexity of project system, reliance on construction accuracy, errors in design calculations, unforeseeable events that which can be predicted, contravention of instructions, then unclear contract information, inadequate load behavior, inadequate connection elements, and poor construction methods or procedures. So it is seen that the major contributors are poor construction procedures, inadequate connecting elements, and inadequate load behavior. So that's all. We'll continue the next in our next class. So those who are here can give the attendance. So those who are here can give attendance now in the chat box. Thank you. Those who have given their attendance can leave the class. Thank you.